Hello friends, welcome to Optics Anand tutorials. Today we are going to see the very important questions based on this semiconductor physics. Okay, this is unit 2 semiconductor physics for the B.Tech first year students, applied physics. Okay. Now, in the previous class, if you see in the previous class, you can simply understand this today's concept, whatever we are going to see. Okay, now we are going to see what is the definition of Fermi level, what is mean by Fermi level, what is mean by Fermi energy. Okay, that we are going to see clearly. Yeah. So, Fermi level, as we explained in the previous class, we already explained this is a conduction band and this is a valence band. And there is a Fermi level is there, and there is a Fermi level, okay, and that level always lies between in between conduction band and valency band, okay, and that at the center of the forbidden gap. Fermi level అనేది ఎప్పుడైనా forbidden gap యొక్క center లో ఉంటది, and that will be lies in between conduction band and valency band లో ఉంటది. So, Fermi level nothing but what you can see here, the highest occupied energy level at 0 Kelvin is called the Fermi level. The energy corresponding to the Fermi level is called as the Fermi energy, and this is very important. The highest occupied energy level at 0 Kelvin temperature. For example, P type N type చూసినాం మనం previous class లో. ఆ P type లో ఏమన్నది హోల్స్ ఆర్ మెజారిటీ ఛార్జ్ క్యారియర్స్ అన్నాం. అంటే హైయెస్ట్ ప్లేస్ ఆక్యుపైడ్ బై హోల్స్ ఆర్ ఆక్యుపైడ్, సో దట్ ద హైయెస్ట్ ఎనర్జీ ఆఫ్ ది P type సెమీకండక్టర్ ఇస్ నథింగ్ బట్, అందుకే మనం ఏం చేస్తున్నాం, ఆ ఫెర్మి లెవెల్ అనేది వ్యాలెన్స్ బ్యాండ్ దగ్గరలో చూపించినాం. వెన్ ఆర్ ద లెవెల్ ఫెర్మి లెవెల్ ఆర్ దట్ ఈస్ యాక్సెప్టర్ ఇంప్యూట్ లెవెల్ ఈజ్ వెరీ క్లోజ్ టు వ్యాలెన్సీ బాండ్, దాన్ని బట్టి అర్థమైంది మనకేమర్థమవుతుంది. సో ఓకే, హోల్స్ ఆర్ మెజారిటీ ఛార్జ్ క్యారియర్స్ అని చెప్పారు. ఓకే, సో కాబట్టి ఫెర్మి లెవెల్ నథింగ్ బట్ ఇట్ ఓకే హైయెస్ట్ ఆక్యుపైడ్ ఎనర్జీ లెవెల్ ఎట్ 0 Kelvin టెంపరేచర్ అని చూస్తాం. సో ఇన్ సెమీ కండక్టర్స్ వీ హ్యావ్ టైప్స్ ఆఫ్ కరెంట్ క్యారియర్స్ లైక్ ఎలక్ట్రాన్స్ అండ్ హోల్స్ ఉంటాయి. మనకు సెమీ కండక్టర్స్లో కరెంట్ ద్వారా కరెంట్ పోతుంది అండ్ హోల్స్ ద్వారా కరెంట్ పోతుంది, బట్ కండక్టర్లో మాత్రం ఒక ఎలక్ట్రాన్స్ ద్వారా మనకు కరెంట్ పోతుంది. అర్థమవుతుందా? రైట్. కరెంట్ ఫ్లోస్ ఇన్ ఏ కండక్టర్ ఓకే డ్యూ టు ఎలక్ట్రాన్స్ ఓన్లీ, బట్ కరెంట్ ఫ్లోస్ ఇన్ సెమీ కండక్టర్ డ్యూ టు హోల్స్ అండ్ ఎలక్ట్రాన్స్. సో దిస్ ఈజ్ వాట్ వీ కెన్ అండర్స్టాండ్. Yeah, listen to me. And in the beginning, before we apply an external electric field or energy to the material or atom, so and before moving the electrons from valency band to conduction band, the electrons are combined with a hole and and they will be disappear. So this is the concept we need to understand. So what is the definition of the Fermi level and Fermi energy? Now let us see, explain the Fermi energy and Fermi level. Okay, the question may be asked like this, and we may be asked like show that the variation of Fermi level or Fermi function with a energy at 0 Kelvin and at a high temperature. So this is also very important, you can see. So in order to show the variation of Fermi function అంటే ఇప్పుడు ఏంటిది, మనం ఫెర్మి లెవెల్ అండ్ ఫెర్మి ఎనర్జీ అనేది మనం డిఫైన్ చేసేసి, సో ఫెర్మి ఫంక్షన్ ఎక్కడ 0 Kelvin దగ్గర ఎక్కడ ఉంటుంది, హై టెంపరేచర్ దగ్గర ఎక్కడ ఉంటుంది అనేది మనం షో చేయాలి. అది షో చేస్తే మనకు ఆన్సర్ అయిపోయినట్టే. సో ఇన్ ఆర్డర్ టు షో దాట్ ద వేరియేషన్ ఆఫ్ ది ఫెర్మి ఫంక్షన్, సో వీ నీడ్ టు గో త్రూ ద Fermi Dirac probability distribution function, that is P of E is equals to 1 by 1 plus e to the power of E minus EF by KT, and this is what P of E is equals to 1 by 1 plus e to the power of E minus EF by KT. So this is the Fermi Dirac probability distribution function by which we can get our solution. Yeah, here P of E nothing but probability of an electrons occupying at the energy state. probability of an electron occupying at the energy state. Okay. Now, let us move to the next. Yeah, wait. Okay. Yeah, EF nothing but Fermi energy, K nothing but Boltzmann constant, T nothing but absolute temperature. So here let us see first. First case is, what is the first case? Here case 1 is, if or for T is equal to 0, if E greater than EF. E nothing but we are applying some energy, EF nothing but Fermi energy. Whenever the applied energy is greater than Fermi energy, okay, it means what? E greater than EF nothing but whenever the applied energy is greater than Fermi energy, at 0 Kelvin temperature what happens? At 0 Kelvin temperature what happens? So from the P of E is equals to 1 by 1 plus e to the power of E minus EF by KT, you substitute these terms or words in the expression, above expression, you will get. Okay. So listen to me. Alright. So here 1 by 1 plus e to the power of E. Here EF is neglected because it is smaller and E will be there. So that is 1 by 1 plus e to the power of, okay na, E by KT. But T equal to 0 here, absolute temperature is what? 0. So that's why E by K, E by 0. Okay, now E by 0 nothing but what? Something by 0, infinity, then e to the power of infinity becomes e to infinity. Okay, 1 by infinity, yes, it is infinity, e to the power of infinity nothing but infinity. So 1 by infinity is equals to what? 0. That's why the probability of electrons at the energy state, okay, that is 0 whenever this condition is possible, right. Next, if you see, okay, and that's why we can say no electrons can have energy greater than the Fermi energy at 0 Kelvin. It means that all energy states above the Fermi energy are empty at 0 Kelvin. If you see the second case, for T is equal to 0, if E less than EF, okay, here which is less than? E is less than, so that E will be neglected and EF will be there. So that P of E is equals to what? P of E is equals to 1 by 1 plus e to the power of, okay, E minus EF by KT, So E minus, E will be neglected, then minus EF by KT, okay, by KT. Here K is equal to what? Boltzmann constant, and T nothing but 0 here, absolute temperature. So that minus E by 0, then we get same e to the power of something by minus something by 0 nothing but infinity, okay, minus infinity. E to the power of minus infinity will get 1 by e to the power of infinity, that e to the power of infinity goes to the numerator and we get e to the power of infinity by 1 plus, or this is e, okay, e to the power of infinity plus 1, and this is e to the power of infinity by e to the power of infinity gets cancelled, remaining will get 1. Okay. The probability of electrons at the occupied energy is P of 1, that is 1. So it means what? All electrons occupy energy state below the Fermi level, below the Fermi energy at 0 Kelvin. చూడండి, absolute temperature 0 ఉన్నప్పుడు 0 ఉండి, okay na, and if energy is below the Fermi level, then there is a probability of electrons having occupying the energy. So if okay, absolute temperature is 0, but energy is more than the Fermi energy, no, there is no possible to have the electrons occupy energy state. Okay, there is third condition. For T greater than 0, then E is equal to EF. E is equals to EF. Then what happens? Here T nothing but absolute temperature is more than 0. More than 0 nothing but we are giving some temperature for the semiconductors. So what happens? Our energy, whenever it is equal to the Fermi energy, and then the temperature is gradually increases. Okay, what happens? And there is a electrons which moves from valence band to conduction band, valence band to conduction band. Clear? Right. you can see here, yeah. So, if you, yes, apply for this third case. So, that is 1 by 1 plus e to the power of e equal to ef, nothing but instead of e you can write ef, or instead of ef you can write e. So, that I am writing e instead of ef, so that e minus e, actually it is e minus ef by kt, you know, instead of em I am writing e by kt, okay. And e minus e gets cancelled, so that it is 0 by kt, something by 0, sorry, 0 by something, this is 0 by something. So, 0 by something is 0 only, e to the power of 0, okay. E to the power of 0 nothing but what, gets 1. So, that 1 by 1 plus 1 is equals to 1 by 2. So, 1 by 2 nothing but off, nothing but 50%, okay, 0.5. So, this tells us the Fermi level lies between conduction band and valence band at the center of the forbidden gap. And also this tells us the number of electrons and holes are same or equal in a intrinsic semiconductors. This is very, very important concept, otherwise we cannot understand the further topics. Clear? Right, listen to me. Yeah. So, Fermi energy level represent the energy state with a 50% probability of being filled if forbidden gap does not exist in the case of good conductors. This is a very, very important concept. The Fermi function is shown in the figure for different temperatures, at 0 Kelvin temperature, at high temperature. If you draw the Fermi function for this graph, you can see, okay, this is at 0 Kelvin temperature is 1, we got it at 0.5, probability of 0.5, okay, here, and probability of 0, P of e equal to 0 at here. So, this graph is tells us a Fermi function, okay, for these 3 cases 1, 2 and 3. So, this question is also very, very important. The question may be asked like this already, okay, we have seen the question may be asked, okay, how explain the Fermi energy and Fermi level and show the variation of Fermi function with a energy at 0 Kelvin and at high temperatures. So, next class we will see in the next topic. Until then, bye, and do subscribe my channel for the more updates. Thank you.